My name is Rotella. I'm going to be telling you about my work on unsupervised contact learning for humanoid estimation and control. So the questions that we want to answer in this work are: when is contact relevant, and how do we define contact? So contact is relevant first of all for base state estimation, where we use the relative pose of the base to the foot to constrain our estimation, and for full body control, where we use contact constraints to constrain our inverse dynamic solvers and render them solvable. So in both of these frameworks, we only allow hard constraints, which means that we end up having discontinuities in our estimation and our control. So here we'd like to come up with a method of continuous contact switching if possible. So how is contact normally defined? Well, usually people just take a threshold on the normal force. So here's a point foot about to touch down on the ground. You can see the force on the bottom. When it reaches a certain threshold, which we arbitrarily choose, we say that the foot is now in contact. But really we don't want to know just when the foot is touching the ground, but when it can actually support creating forces in different directions without the foot slipping. So for that we'd have to consider the friction cone as well and look at the lateral forces and keep them within these cones. But it's actually a bit more complicated for a humanoid because we also have the center of pressure constraints, which we would also need to model. So that said, there are a couple of ways that we could go about contact estimation. So we could use models of the friction and the center of pressure and try to learn the parameters that govern them, but instead we want a contact estimator which is completely unsupervised and model-free. We'd like to use only internal sensing so that we're not dependent on something like Vicon or ground truth for contact, which is exactly the thing that we don't know. And we want to estimate continuous six-dimensional probability in all 6 dimensions of the end effector. So looking a little closer at the constraints that we talked about, slip constraints are governed by the the reaction force and the coefficient of friction. Rotation constraints are governed by the center of pressure bounds and the full contact wrench. So the idea here is that we can add an IMU to the end effector that will tell us if the foot is slipping or rotating, and then collect data with the contact wrench and the IMU acceleration and angular velocity, and use this to perform unsupervised learning to come up with contact estimators for all 6 dimensions independently. So then we can use this contact estimation to tell us when to use different estimation measurements in our base state estimator. And we see that actually if you use the probability in the base state estimation, you can reduce the state error in position and yaw considerably, versus if you used a fixed threshold.